All right, so yeah, thank you. So I'm going to talk today about script and its memory hardness. And this talk can be really seen as a continuation of Jeremiah's talk, in the sense that I'm going to tell you the other half of the story about memory hard functions. And in particular, talk about data-dependent memory hard functions, and which script is one example. So, and I should mention, this is joint work with a set of amazing co-authors, Joel Alvan, my PhD student, Bini Chen, Czesto Pieczak, and Leo Rezin. Leo and Joel are also in the audience. You can also certainly ask them questions about it. So I don't need to introduce the concept of a memory hard function anymore. So in particular, Jeremiah has introduced the notion. And let me just do one thing here. I have a problem with the screen. All right. So I don't need to introduce the notion anymore here, but for those of you that missed the talk or just came in, just think of them as moderately hard hash functions to be used in the context of password hashing or key derivation or proofs of work, where moderate hardness is in terms of both time and, most importantly, memory consumption. And there have been numerous practical designs that have been just mentioned that targeted memory hardness, like script and Argon2D, Argon2I, Catena, balloon hashing, and many more. But the focus of this talk is going to be on provable security once again. So in particular, provable security has been very effective in validating real-world cryptography because it helps us in gaining extra confidence, in particular against those attacks that we cannot envision yet. But somehow, in the context of memory hard functions and the password hashing competition, where many of such designs have been proposed, things went a little bit differently, mostly because we were lacking appropriate theory at that point in time, or at least that's my assumption. And validation there has mostly occurred in terms of cryptanalysis and often enough intuition. And as you have just seen, there is now better and better theory to validate memory hard functions. But we're still somewhat on a quest to find practical design that are also provably memory hard in the strongest possible sense. So, and if you want to close this gap, of course, there's two things you might try to do. So one of them is what was advocated in the previous talk. So we have a well-defined theoretical framework to design provably secure memory hard functions. And we want to find those that are practical enough in this framework and that can be deployed. But another alternative, which is what we do in this work, is that you can look around for designs that exist already in practice, but that are out of reach for current techniques, but they resist attacks, and maybe try to come up with a valid theory that proves them secure and memory hard. And this is exactly what we did in this work, and we targeted script, and the main message here is positive. So we provide a proof that the script function is optimally memory hard, or ideally memory hard, using the language from the previous talk. And this is particularly surprising at first because, well, script was the very first candidate memory hard function. It was introduced by Colin Percival in the very same paper in 2009 that introduced the notion of memory hard functions as we know it now. It has found usage, so it is the object of a recently published RFC. It is also used within cryptocurrencies for proofs of work. It's using Litecoin and other lesser cryptocurrencies. And also, it inspires other designs. So you can find ideas from scripts, for example, in Argon2D, one of the two winners of the password hashing competition. And let me stress really that, I mean, this is interesting in practice, but also from a theoretical standpoint, this is the first example of memory hard functions that we can prove optimally memory hard. So even in theory, not just in practice. So let me put this a little bit in the context of the previous talk. A lot has been said already. So I guess the main point here is that we distinguish between memory hard functions that are data-dependent and data-independent, right? So data-independent ones are those where the memory access patterns during the execution can depend on the input, whereas cannot depend on the input, whereas for data-dependent, they can depend on the input. And script, like Argon2D, is an example of a data-dependent one. So far, the theory has been really focusing on data-independent designs. Now, sure enough, one reason is they have some attractive features that I'm going to talk a little bit more later, resistance to side channels, if you're concerned about that. But a major point is also that from a theory standpoint, there's a much cleaner connection to graph pebblings that Jeremiah has just illustrated that makes proving things much easier. On the other hand, even though we have this framework in place, coming up with practical designs, as you can see, is work in progress, right? And we have, even though this is the object of some controversy, but we have attacks now that definitely show that there are structural weaknesses in practical designs that we already have. On the other hand, on the data-dependent side of things, there's quite a lot we don't understand. So we have designs around like script and Argon2D that seem to resist any non-trivial attack and speed up. On the other hand, we have absolutely no theory to understand why that's the case, and they seem much harder to tackle. And so that's exactly what we were concerned with here. So a little bit more concretely, what we target when I say we analyze script, we actually target an analysis of what is called row mix, which is the core of the script function. And it's a hash function, which is a mode of operation for a simpler hash function, which is not quite a hash function in the usual sense. It's built out of salsa, and it's length preserving. But I'm going to abstract this as just a hash function h. And the structure is very simple. So it starts with a simple iteration of a hash function, of the hash function h. So you have an input, m. It's going to become your first state, x0. Then you iterate the hash function to get n values, x0 up to xn minus 1. And then you apply the hash function once more to get what is the initial state of the second stage. The second stage is where the interesting things happen that ensure memory hardness. In particular, we start by looking at the initial state as 0. Maybe you can't read it from far. It's a little bit small. But what you do is you now want to derive an integer between 0 and n minus 1 from the state as 0. You can do that, for example, by interpreting s0 as an integer and then reducing it mod n. And you interpret this as an index which points to one of the n values, x0 to xn minus 1. Say it points to 1. So you're going to take that value, and now you're going to XOR it into the state, apply the hash function again, and then you get the next state. And so you can go on like this. So you're going to do the same thing to the next state, derive an index, say in this case by accident is the last one, take that value, XOR it into the state, and go on until you get the final output. Now you have some parameter n here. There's no clear discussion, I think, what are the right parameters for script. I think suggestion I've seen are things like n is equal to 2 to the 14. W, which will be the length of the hashes, so the size of the state, should be something like 1 kilobyte or larger, but I think by today's standards you might even want to have larger parameters. All right, so we want to analyze this. We want to prove it memory hard. What that means is that we would like to prove a lower bound on the cumulative memory complexity. That was already introduced in the previous talk. So informally, what it means is that we want to show that for every adversary, even parallel ones, if we take the integral of this curve, so we look at the memory consumption at every point in time, and we sum them up, we want to show that this is large enough. Okay? And this is lower bound for another metric which is less appropriate since it's less resilient to amortization, which is the ST complexity, which just looks at the maximum memory consumption times the time complexity. So, and we want to prove this, and somehow we are very bad at proving lower bounds, usually in crypto. So what we need to do in this case is, or the usual way out, is that we are going to make some ideal assumption on the underlying hash function h, and we model it as what we call a random oracle. So we model it as a random hash function. And then we just want to prove a lower bound on any parallel adversary that tries to evaluate row mix in this model. That means we consider some adversary that takes as input a message on which he wants to evaluate the function, and then proceeds in steps where in each step, what it can do is it can submit a vector of queries, so multiple parallel queries simultaneously to the random ideal hash function, and also can keep some state for the next step. And then in the next step, the adversary is going to get this state, is going to get the responses to these queries, and then do this over and over again, and then just output something which ideally should be, if the adversary is correct, for evaluating this, the function should be the output of the function on input m. Right? And then we want to consider the cumulative memory complexity of such an adversary, which typically we're going to model the memory size at every step by considering the size of a state as I, and plus we're also going to consider the size of the answers that the adversary gets back from the hash function queries. This is very generous. The adversary might need more memory, but we're going to prove a positive result, a lower bound. So it doesn't matter. If the adversary uses even more memory, then that's better for us. Okay, so if we think about this metric now, and we want to evaluate row mix, now there are two naive approaches that you could take to evaluate the function. Okay? So the first one is you can just consider a naive sequential evaluation, which is what you will do when you run your function on your computer, which is you simply compute the values in the first phase and store them into memory. And then when you get into the second phase, what you're going to do is you're just going to take them from memory whenever you need them and they're going to be there. And hence, you can compute through the entire thing in linear time in a parameter n. And the amount of memory that you need, well, it's as much memory as you need to store these n values that are w bit large. So if you think now about our cumulative memory complexity, you have a linear number of steps. You can store up to n times w bits. So the cumulative memory complexity is going to be n squared times w bits, right? Roughly. I'm omitting constants here, okay? Now, the other alternative strategy is that you say, well, I don't want to waste any memory now, and I want to do this with almost memoryless. So what you could do here instead is say, okay, I'm just go through the chain at the beginning and don't remember anything, get to the initial state of the second phase, and now see which value I actually need. Say, for example, now I see, oh, from my S0, I need the value x1. So now I'm going to recompute it, starting from x0, and I'm going to get that value, and then add it into the state, and then forget it, and go on. And then see what's the next value. I'm going to recompute it, and then just add it to the state and go on. Now, this recomputing can be expensive because we might have to do up to linear work to go through the chain again. So on average, say, n over 2 steps. Okay, so overall, we make n squared steps. And however, the memory we keep is very small, so of the order of w bits, where w is the size of the state. Remember. So again, the cumulative memory complexity is something like n squared times w. Okay? So now we can start making some conjectures, which is what people have conjectured for long, which is that we have two extreme strategies, one remembering everything sequential, the other one memoryless. So we could conjecture that now every other strategy might be at least as bad, right? But of course, they're just a conjecture, and we really have no, a priori, we wouldn't have no evidence, right? It could be that the real thing is like this, okay? So maybe there are some strategies that are much better than n squared times w. Okay, I know the plot is a little bit absurd, but it was kind of a theory talk, so I thought I should put some plot just to make it more real-worthy, I guess. All right, so is the conjecture true or not? And so that's exactly what we confirmed. So we confirmed that the conjecture is true, at least up to some multiplicative factor. So what we show is that roughly for every possible adversarial strategy that wants to evaluate row mix, its cumulative memory complexity is going to be, well, roughly n squared times w times a constant, which is 1 over 25, and could be up for optimization in our proof. And also note that we don't quite get n squared times w. We get n squared times w minus some difference, which is 4 times log n, where n is the parameter that gives you the number of iteration. This is somewhat inherent in our proof technique. So there is a small loss even there, even if you optimize the constant in front. So we really can't get rid of it. But note that it's not a big problem if you're concerned about a concrete parameter, especially because typically w is quite huge, something like 1 kilobyte at least. And log n should be at most 14, so you should not really be concerned too much about that for log n. Okay? Also note that despite the simplicity of this result, this is really not something easy to get. There have been numerous, at least a few attempts to prove this result in the past. For those of you who actually read Colin Percival's paper, I assume many of you, introducing script, there is actually a proof there of memory hardness for script. And it turns out, I mean, I'm not going to go into it. We have more evidence to it in the paper, but it's pretty much folklore by now that the proof is incorrect. So there is a bug there. And also it targets a weaker security property than a weaker hardness measure than cumulative memory complexity. And there's also some previous work by myself and a partially overlapping set of co-authors that appeared at Eurocrypt last year, where we proved a weaker bound and for script. And that's weaker both quantitatively, it falls short of being optimal, and also it only holds for restricted adversaries. So I'm not going to go into it. Now, the important point here that was already addressed by Jeremiah is that this shows a separation between data-dependent memory hard function and data-independent ones. So by a result by Jeremiah and Joel Alven, we know that for every data-independent memory hard function, there exists a strategy that allows you to evaluate it with cumulative complexity, which is roughly n squared times w over log n. Whereas here, we prove something of the order n squared times w, so there is a log n gap that is going to fall away. Of course, we have to be honest here, constants here matter, and a log n and a constant factor might end up being the same for reasonable n's, but at least asymptotically, you see that the difference can be substantial, and with a similar constant, you have to be careful about that, because log n can be very large for reasonable parameters. So why is proving something like this so difficult? So the main reason is that we are quite bad at dealing with bounded memory in provable security. And we have to address the fact that an adversary that might evaluate this function arbitrarily, we want to show that it's hard for any possible such adversary, tries to memorize partial information about the execution and could do whatever it likes to do that. And so these states, these intermediate states, could be really arbitrary, and we have to think about that. In the IMHF case, the proof was much simpler somehow because the very nice, elegant reduction to graph pebbling works. The problem is that this trick really requires you that the data dependencies in the computation are all known a priori, something which we don't have here. In fact, the security of something like ROMIX or Scrypt or Argon2D really depends on data dependencies being unpredictable. Otherwise, you cannot get as high security as we get. The intuition, indeed, is that the reason why this thing is memory hard is that once you move to the second stage, these indices that you have to go fetch, for which you have to go fetch values from the first phase, are unpredictable until you compute them. And so in order to be ready to proceed fast, you need to have many of these values stored in memory already. Otherwise, you're going to be stuck and need to recompute things. And so that's why the intuition, I just want to give you a 5-minute intuition about why Scrypt is memory hard, is to really think about the following game where you're thinking about the evaluation of ROMIX. Think about having a game between a challenger and an adversary. The adversary learns the initial value x0, can make queries to the random hash function, the random oracle, and now the challenger in the game proceeds in rounds, and on each round gives to the adversary a random challenge, which is an integer between 0 and n-1. And the goal of the adversary is to come up with possible using as few memory bits as possible with the value indexed by that challenge in the initial chain. Okay? So I'm abstracting away completely the second phase of ROMIX with the idea that it's really about getting these challenges that are unpredictable and going and fetch that particular value. And now the adversary wants to go through all of the challenges and be able to compute. So in fact, we can make an extra step here just for the purpose of this talk, which is very intuitive, and even model a simpler version of this game where the adversary only remembers, similar to the pebbling case, just the values, x0 to xn-1, or a subset of them. And so we can really think of this also as a special case of a pebbling game, or a variant of a pebbling game, where we look at the line simply, and putting a pebble on a particular node on the line with nodes from 0 to n-1 indicates remembering the corresponding value xi if you have a pebble on node I. And then you have the same rule as in the pebbling game we had in the previous talk. And in particular, multiple moves can be done in parallel. So something the adversary could do in trying to evaluate, it will start by putting always a pebble on the first node. Then it could add pebbles, it could move pebbles, and always put a pebble next to a pebble which is already there, and move in parallel to support parallelism of the strategy. Right? And so in particular, the challenge, the round game with challenges in this setting will simply have now the adversary learning a challenge at every round, say for example here 4, and now the goal is to put a pebble on 4. For example, now this will be done in 4 steps if you don't have anything on the line, because you have to start by putting a pebble and then move step after step. Then say you get another challenge, now you have to put another pebble, move there into step, but now if you get another challenge on 6, now you're lucky, you have a pebble nearby on 4, and you can move fairly quickly to 6. Right? And you're interested now in seeing what's the complexity of an adversary to go through this game. And in particular, note here that the memory complexity at a particular stage corresponds roughly to the number of pebbles times the number of bits to store a value. And now, we want to lower bound the complexity of any strategy that successfully goes through this game. And again, this is completely arbitrary. The strategy could do anything. So it could have different amounts of pebbles at different stage. Whenever it gets a new challenge, it could have a different number and a different subset of pebbles on the line. And it could take different amounts of times to answer that challenge. And still, we would like to show that no matter what we do, there's a lower bound which is squared in n for the curve here, which is defined by the red lines. So this is the core of our proof. And the basic idea here is that whenever you have a certain pebbling configuration and you learn a challenge, the time you need to answer that challenge is inversely proportional to the pebbles you have on the line. This is quite natural because if you have a certain set of pebbles, I have so much time? Okay. Oh, 5. Okay, good. So Yeah, I think I'm going to be faster. So if you look at the set of pebbles that you have here on the line, there could be anything. Say you have P of them. And now you want to see how many challenges you could answer within a certain amount of time steps, say 2 time steps. In fact, we count these as 3 in the paper. Then there are only so many challenges, so any challenge that lands into this highlighted area could be answered within 3 steps. Anything else requires more time. And so if you do the math, what you see is that this gives you a very nice probabilistic trade-off, where we see that, at least with probability 1/2, the time that you need to answer the challenge, the probabilities over the choice of the challenge, is at least n over, or larger than n, over twice the number of pebbles you have. Or in other words, what that means is that with probability 1/2, you have a trade-off in the form that the time you need to answer the challenge times the number of pebbles that you have on the line is at least n over 2. Right? So this takes us much closer to what we want, but we are not quite there yet. In particular, what this means, now assuming that this trade-off, just for the simplicity of my explanation to make it simpler, holds for every challenge, what this means is that if we look now at the amount of pebbles that the adversary has on the line every time a new challenge is revealed, and now we look at the rectangles that are defined by taking as a height this number of pebbles, and the width of the rectangle is the time it takes to answer that challenge, then what this trade-off tells us is that the area of these rectangles, of all of them, or at least all of them for which this probabilistic trade-off holds, is at least linear in n. So if you have n challenges, now it's intuitive to think that the overall area should be n squared. Unfortunately, that's not quite what we need, because we need to look at this curve, which is defined by the amount of pebbles we have at every time. And we have no guarantee that after an adversary learns a challenge, it might just not drop everything it has and just remember, for example, the closest pebble to the challenge and forget about everything else. In fact, for the last challenge, for example, that's the most reasonable thing to do. Everything else will be rather stupid. So what that means is that the area, which is the blue area here, is n squared, but we need to lower bound the area which is defined by the red histograms. Now, I'm not going to go into details how we do this, but the basic idea, and that's one of our 2 major technical contributions here, is to look not at the area that we have under the curve after the challenge is revealed, but to realize that in order to have a number of pebbles which is fairly high, then we need to put them there. And so there is some work that we need to do. And so what we look at is not at the drop or the behavior of the curve after we learn the challenge, but we use a generalized version of the trade-off to look at what happens before we learn the challenge. The other main challenge, of course, that I haven't talked about is that here I am looking at the simplified version in terms of pebbling. But obviously, we want to deal with adversaries that can store any type of information about the previous states of the execution. And that requires some more technical work, which I'm not going to talk about here. But that's very important. Now, I have some lengthier conclusions here that I want to start going through. So the first one is that I think this is it's an important result because it's a good example of an interesting theory problem that, however, validates a very practical design. I just have a quote here from Phil Rogowitz's essay on the moral characters of cryptographic work, where, in fact, he motivates this as an important line of work to try to understand these modes. But that's not the only one thing here. So it gives also a very good example of a practical design with strong provable memory hardness guarantees. And also the first one, which is really practical and has such provable guarantees. And also, it's really the first example, even in theory, of an optimally memory hard MHF. Now, a question you might ask, because I've been focusing on scrypt and ROMIX, is what about Argon 2D? So Argon 2D, for those of you who are familiar with it, has a very similar design to scrypt. The main difference being that you don't have such 2 phases of execution, but you have a sliding window of values that you're going to use and point back to insert in the execution. Now, we don't have this written down in the paper. That's why I have a star. But the same technique should easily give the same lower bound. But so we don't have this in written yet. Okay? Now, another thing that I wanted to say is that also came up in the previous talk, is about the issue of DMHFs versus IMHFs, so data-dependent memory hard function versus data-independent memory hard function. So at least with respect to the goal of achieving high and optimal memory hardness in a provable sense, so DMHF seems to be easier to get right and also provably achieve a higher memory hardness, at least in an asymptotic sense. So the main problem here that you might face, despite the fact that they're also harder to prove memory hard, but other than that, of course, the main concern are side channels. And this is something that was also mentioned by Jeremiah. They are a possible concern. Your memory access patterns do depend on the input. And so here, the main point is that you should be really assessing whether in the application you're looking at, you're more concerned about memory hardness being strong, or whether you're concerned about possible side channels. So there are applications like proofs of work where for sure side channels do not seem relevant at all. For password hashing, well, you have to see. But if you're not concerned about that, then there's really no reason why you shouldn't be using data-dependent memory hard functions, since the guarantees really seem to be stronger. And finally, just a few words about proofs. So I really think that there's been some debate, also for those of you that follow CFRG, on the role of proofs in the context of memory hardness. I really think they are important. So if you have a mode that has a proof and is as efficient as one without, I don't think there's any reason to discard the one with a proof. Of course, it's not the only thing. There's a lot of interesting questions related to how tight these proofs are and whether the models are the best ones. But still, I think the proof remains an important component. And of course, when I say proofs, I mean you have to target concrete security and be as concrete as possible, especially in this domain where speeding up things by a constant factor really matter and makes an impact. You have to really work and make an effort into having bounds that are as tight as possible. Okay, so that's actually everything I wanted to say. So there's a paper on ePrint about the results, so feel free to have a look.
With a quick question. So there was a constant in front of your bound, right? So does that give any inspiration for a new attack that would be a small constant factor speed up?
I don't think this is really tight. I mean, there's many ways of like relaxing things in the proof that might make things a little bit better. So for example, just requiring that the usage of memory is slightly higher throughout the proof. So it's not clear, really. And there's some work there that should be done and try to tighten them up. So I don't think 1/25 is the final answer.